It is my honor to present our next speaker, who is Professor Harry Collins. He's a distinguished research professor in the School of Social Sciences at Cardiff University, and he is a fellow of the British Academy. He has authored or co-authored numerous books. I counted 17 on his Wikipedia page.
26.
26, oh, that has grown. 26 books and hundreds of scientific articles. He has written for over 30 years on the philosophy and sociology of gravitational wave physics. His first book, Change in Order, Replication and Induction in Scientific Practice, is, at least for me, one of the most influential and important books in the so-called experimental turn in the philosophy of science. Already in 1975, Professor Harry Collins identified much of the problems with replication before almost 30 years before the replication crisis. So, Professor Collins, the floor is yours.
Well, thank you very much for inviting me to this meeting. I'd really hoped to be able to come in person and enjoy some sunshine after the terrible winter here in the UK, which we always have. But it's good to be here because I think this is an interesting topic, and it seems to me to be very badly misunderstood in some important respects. As our host said, I've spent about 45 years of my life immersed in the attempts to detect gravitational waves. And that has informed a lot of my thinking over the years, though, including the book that our host mentioned. But I've since learned a lot from watching the gravitational wave physicists doing their work. And I'm going to try and provide some of the lessons here. So now let me see if this... End of slideshow. Oh, yeah, end of slideshow. Yes. Sorry about this. Blow. Sorry, I'll sort this out in a minute, I hope. How can I do this? Right, I've got some sort of error here. I'm going to have to try and get out of screen sharing and come back into it. Sorry about that. Don't usually get these technical problems, but we've certainly got them today. It's all my fault, I'm sure.
That's okay. We can see your slides. I think the first, no.
Oh, wait a minute. How's that? Wait a minute. That's better.
That's better. But if you go to the slides,
it was okay before.
It was okay. So you go to slideshow.
Oh, how's that? Can you see that? Can you read that?
Yeah.
But not in the full screen. Is it okay?
No. You can do better.
Yeah, you can go on slideshow. Just
you prefer that?
Yes.
Yeah.
Okay.
Okay, and then
the only trouble is I've got to be able to see it. Right. Okay. Let's try this. Can you all read that?
Yes.
Yeah. Perfect.
Right. So how should you choose the level of statistical significance that entitles you to publish something as a discovery? Well, I'll suggest a method. The ideal method would be to do a meta-meta analysis. Execute lots of sets of experiments to different statistical standards and see which standard ensures an acceptable level of repeatability. Well, it happens that over the decades, physics has done this. Not deliberately, not with this intention, but it's just done it so that physics has found that a reasonable level of statistical significance, if you want repeatability in your experiments and want to be able to claim something as a discovery, is 5 sigma. That's 1 chance in 3.5 million of the result being due to random sampling error. Physics has increased from 3 sigma in the 1960s through 4 sigma in the 1970s, and was at 5 sigma in 2016 when the first detection of gravitational waves was accepted for publication as a discovery. So it's done an inadvertent experiment for us all. Never intended to do this, but what it shows, obviously, is that unless this experiment has just gone completely wrong, that sciences that adopt a less demanding statistical standard for publication have always been at risk of non-reproducibility, and the actual non-reproducibility should have come as no surprise to anybody. I mean, I can't understand why people haven't noticed it, why I'm the only person to have noticed this, that it's always been obvious. I can't see any reason why the statistical standards for physics, for shall we say psychology or sociology or indeed medicine, should be any different to those for physics. But nevertheless, people sort of treat them as different because, well, it's because, as we know, mostly these other sciences couldn't reach 5 sigma. If they reach 2 sigma, they're really delighted. But it should have been obvious to everybody for years as a result of physics' experience that things were going to go wrong. Furthermore, my experience of physicists is that they are acutely conscious of all the things that can go wrong with a statistical calculation. Indeed, they are so conscious it gets to the point of craziness with physicists. I'll give you my favorite example, which you'll find written up in my books on gravitational wave detection. And this is a famous thing, well known among the physicists themselves as well as crazy, at least some of them think it's crazy, called the aeroplane event. One of the rules that the physicists in gravitational wave physics use is not to do retrospective statistical manipulation. But they know that in order to work out the best way to statistically analyze an experiment, you have to do some tests on real data to see what is looking good. So they have a rule which says we're allowed to do the tests on these data on what's called the playground. And the playground is a small subsection of the data as a whole, say 10% picked randomly. So they do their experiments on the playground until they find statistical techniques which seem to work pretty well, or the best statistical techniques they can find. And then what they do is open the box to all the data. And then they do the analysis. And their rule is they must not make a change in their protocols after they've opened the box. Well, in one of the famous observations, they went through this procedure and then they opened the box, and then they discovered that there was what looked like a kind of signal in the data, but they found out that that signal coincided with an aeroplane flying low over the interferometer. So they knew that signal was caused by an aeroplane, but there was no rule developed when they were working with the playground which allowed them to remove an aeroplane. They hadn't thought of it. And so some people said, there was this huge long argument, went on for months, saying, we have to leave that data point in the data, even though we know it's an aeroplane. With other people saying, no, that's mad. We've got to take it out because we know it's an aeroplane, even though that breaks our statistical rules. Well, in the end, some kind of sanity prevailed and they took the data point of the aeroplane out. But, you know, there were 1 or 2 people who resigned from the whole project because they thought the statistical protocols had been violated and cheating was going on. So that's how crazy physicists can get about thinking about statistical protocols. And in fact, physicists reaching out to 5 sigma, which they'd done by 2000, well, probably by about 2000, I don't know, 1980s, probably 1990s, is actually their attempt to swap all kinds of systematic errors. They know that even though they have these statistical protocols, they can't get rid of all their systematic errors. One example is the trials factor. So physicists are acutely conscious of the fact that every time you do a new statistical calculation, you're cutting your statistical significance in half. Sociologists and psychologists seem completely unaware of this. They try all kinds of statistical techniques until they get one that works, but they don't do it on the playground. They do it on the data as a whole. Anyway, I mean, the physicists are aware that there may be other people doing other experiments somewhere else, which are causing a trials factor, because you've got to take those other people's experiments into account as well. And if you continue to think about this, you go slightly crazy, because you never quite know which other experiments you ought to be taking into account, which statistical analysis you ought to be taking into account, which statistical analyses refer to the same result, which to a different result, and so on. And I can tell you that there are large arguments about this in the gravitational wave community. And at the end, I'll tell you how you can find some writings about this. Anyway, so they actually got up to 5 sigma, and I have a nice quotation, which I won't read you out here. They actually got up to 5 sigma because they're taking a kind of statistical sledgehammer to all the things they didn't know about what was going on in the experimental domain. And they found that kind of more or less works. It doesn't always work, because there are some 5 sigma results that have turned out to be wrong. And they're acutely aware of these. But nevertheless, it seems to be, acceptable. If you stick to 5 sigma, you've got a big enough effect size to have swamped all these unknowns. But sociologists' use of statistics is laughable by comparison, and psychologists seem happy to engage self-consciously with all kinds of disreputable practices. A guy called David Peterson has studied all this pretty well. So in fact, not only are what I'll call the 2 sigma sciences liable to be non-replicable because physics has shown you need 5 sigma, but they're actually even more likely to be non-replicable because they don't do their statistical protocols don't take their statistical protocols seriously. So the lesson from physics about statistics is, if you're relying on a significance test for your warrant about your result being reliable, be nearly as pedantic. I don't say quite as crazy as physicists, but nearly as crazy as physicists about statistical purity, and accept that many unknowns and enigmas will remain, and the only statistical recourse is to try and swamp them with 5 sigma or more, which, as you know, is pretty well unattainable. And some of the talk about how to resolve the non-replicable problem by meta-analysis suggests, well, maybe we should get up to 3 sigma, but that just won't get there. It won't do any good. But more deeply, in normal science or revolutionary science, the science that I take gravitational waves to be an example of, gravitational wave detection to be an example of, you can't excuse me, you can't improve your statistics by meta-analysis, because experimentation is a skillful and tacit knowledge-laden activity. And therefore, you don't know which experiments are any good and which experiments aren't, which you want to bring into your meta-analysis. So the whole notion of open science actually opens the scientific domain to bad science, people who are doing shoddy experiments without the real skill, the skills needed to do a complicated experiment like that. I mean, the worry among gravitational wave physicists is that all the really skillful people have been gathered into the field. So how can they get peer reviewers, and how can they get critics? And what high energy physicists do, for example, is set up a red and a blue team within the discipline to fight it out among each other. But this is kind of developing artificial critics. And that's what they do, because they know the best criticism is going to come from inside the field. And this is the consequence of the experimenter's regress, which is described in that book that our host mentioned, Changing Order. Deciding what is replicable is coextensive with deciding what is true. And that has to be done in small, trusting groups. Meta-analysis will be mostly a matter of rubbish in and rubbish out in frontier adventurous science. But the lessons from physics may not apply to what we call hypernormal science. There's a paper in press at the moment on the meaning of hypernormal science. In hypernormal science, all the assumptions and skills have been uniformly acquired and accepted by, say, PhD level. So research is a matter of quantity of activity, not the establishment of credibility, like work on a production line or building a wall or whatever. I think probably the sequencing of the human genome is a good example of hypernormal science. It's frontier science, it's research science, but all the people who were contributing to it already had all the contributory skills at their fingertips. Here, open science and meta-analysis may help. Much more important than anything else, it would be a disaster to mistake hypernormal science for science as a whole. It would be a disaster for science and a disaster for democracy. The more open the science, the more does science turn into social media. And you can see this happening with the pandemic crisis. There's a very nice analysis of the science of ivermectin, one of the drugs that Trump was pushing at the beginning, because lots of people did poor experimentation on ivermectin. But because all the results of all these experiments was available on social media, the ivermectin debate was a kind of ideal open science example of open science. Anybody could contribute, and anybody could assess what the science meant. And of course, it didn't produce good science, it produced awful science, and science which could no longer act as a check and balance to maintain pluralist democracy in the face of Trump's populism. So does this mean that the two sigma sciences are doomed? Psychology, sociology, and the rest of it? No, it means the remedy is to shift from statistics and that kind of open science as a warrant to other kinds of warrants based on more scientific understanding. I mean, in some experiments we ourselves did on what's called the imitation game, we got pretty good statistics by aggregating enough of those experiments together, but we still didn't believe them because we knew enough about what can go wrong with statistics from our experience of physics not to trust the results. But you could trust, nevertheless, you could look at the way those experiments unfolded and you could tell they were working. You know, you knew that we'd found something that was valid, not because of high statistical significance, so that was useful to convince other people, but because you could see the way the actual experiment unfolded, and it unfolded exactly as we expected it to. And in another place, I call this the statistical versus the tangible. Anyway, that's all I've got to say. But if you want to read some more about this, the stories about how statistics is used in gravitational waves can be found in this book, Gravity's Ghost and Big Dog. The crucial chapter is chapter 5. And if anybody sends me an email, I'll send them chapter 5. Then there's my methodology book called Forms of Life. And the story about tangibility versus statistics is in chapter 9. I can't send you that because of the commercial reasons, but in fact, I can send you a paper that repeats it. So if you want that paper, send me an email and I'll send it to you. The relationship between misunderstanding science and the survival of democracies is in this book, Why Democracies Need Science. And there's another book coming out, it should be any month now, and it's open access. So I can say I can advertise this without shame that I'm supposedly getting any royalties, though I seem to have very few royalties anyway, ever. But it's called The Face-to-Face Principle, and it explains why science can't depend on social media. And though we don't mention, I can't remember whether we mention open science or not, but you can see the danger of open science by looking at that book. So that's it. Thanks. Hello?
So thank you, Professor Collins, for that great talk. So if you could stop sharing your screen. So
Stop sharing.
Yes, stop sharing.
Okay.
What we're going to do, we're going to take questions from the audience. Hopefully you can hear the audience. Otherwise, I will repeat. Also, people on Zoom can ask questions.
Okay.
Okay, so questions? So Sebastian.
The obvious question, what can we do in...
So hang on, I can't see you.
I'm here.
So there's a camera. No, there's a camera. If you see, there's a camera showing the audience on the Zoom.
Ah, you're in the audience. Okay.
Yes.
Yeah.
Okay. So, like, bit loud. Yeah.
Okay, the obvious question is that most sciences are not gravitational waves, and it's completely impossible to reach 5 sigma on everything that it's not astrophysics. It's not that it's our idea. It's completely impossible.
Yeah.
I'm not speaking about social sciences. I'm speaking about my science, chemistry.
Okay.
So 2 sigmas, fine. 3 sigmas, great. That's it. What can we do?
Well, it depends whether you want the truth or not. Whether you want your experiments to find the truth. If you're relying on 2 sigma and 3 sigma, they won't be reliable. So you can repeat the experiments, not thinking about statistics, not thinking about meta-analysis, but just that anything reliable is repeatable. So you have to repeat the experiments. And I mean, in chemistry, as I understand, there are certainly journals who won't publish methods of synthesis unless the editor has already repeated them. Isn't that right? And that's the kind of thing you have to do. Either that or make a case for why the piece of chemistry you're doing will work irrespective of the statistical analysis.
So
The statistical analysis, 2 sigma, 3 sigma, just isn't going to be reliable. Isn't going to give you a reliable warrant. And you have to accept it.
use another method.
Yeah, I mean, you do more science rather than more statistics.
Fun with that.
Copy and then Uten.
Yeah, I want to follow up a little bit on this question. I'm also a chemist. Let's say I do a synthesis, okay? And the synthesis gives me 80% yield. So this is what I write, 80% yield. But Of course, there's no 5 sigma on that. If I have to have 5 sigma on the 80% yield, I will never publish anything else in my life. I will be all my life working on trying to get whether this 80% yield is the truth or not. Can you say something about that?
Well, what you do, I suppose, I mean, presumably you have some error bars. You don't just say it's 80%.
Yes, but the error bars are not 5 sigma.
No. Well, no. You mean you, or you obviously, what you're saying is that the error, to get to 5 sigma, the error bars would have to be hugely wide to make the result worthless, right?
Exactly.
Yeah.
And
So,
I would have to make so many measures. No, I can repeat the experiment many times, but then this is all I would do throughout my career, and yeah, that would not be good, probably.
well, I think what I would do in that case is, sorry, I shouldn't be giving you advice about chemistry because
No, I want to hear.
But what I would say is you repeat the synthesis half a dozen times, and you just tell people what you got on the half dozen experiments. Sometimes it would be 80%, sometimes it would be 75%, sometimes it would be 60%, sometimes it would be 90%. I don't know. Is that the kind of scatter you'd get? Just show them the scatter.
Yeah.
At least you'd be telling the truth about what you did.
Okay. Thank you.
I mean, do you think that's reasonable?
Yeah, I do 3 repetitions. That's 6, because if not, my students will. Well, not me. I don't do anything in the lab anymore. My students do it, but I guess I tell them to do it 6 times.
Yeah. I mean, I don't know. I just picked 6, but what we're getting at here is that there isn't any magic formula that will, where you can say, I've got 2 sigma or I've got 3 sigma, and that relieves me of all further responsibility because I now know that my result reaches the standards of science.
Right.
That's not how science is. Science is you're doing your best with integrity, and you're passing to the rest of the community what you think is probably right. And half a dozen results. So one of the things that I think is and we've argued this in print, is that scientists are extremely reluctant to put in their papers how many times they did an experiment which didn't work, or how hard it was to do the experiment. And we think that should be part of the write-up. It took us 3 years of trying to manage to do this synthesis. Whereas you won't say that if you publish a synthesis, I don't think. I'm not an expert in chemistry, but you'd say something like, here's the synthesis. You should say something like, and it took us 3 years of trying to get this. And that will give us a different kind of sense of how hard this experiment is, how hard this synthesis is to do. That kind of detail, I think, should go in.
Thank you.
Yes, okay.
Yeah, 2 things. First, can you hear me?
Yeah.
Okay, good. You said something like we should get away from statistics and we should look more closely at scientific practice and experimentation and so on. I completely agree with you, except, of course, that scientific practice includes statistics. I mean, so we cannot really get away from that altogether. But my question here was, are you referring also to Michael Polanyi's idea of you mentioned tacit knowledge or the skills, etc., of the scientific researchers? And the second question, or let's say related question, is, I mean, I have reviewed in history cases in which from the same scientific field, 2 contradictory notions were published for a long time. And of course, philosophers cannot decide who is right or wrong, or historians not for that matter either. But in this case, it was possible to judge from the outside because it was known, I mean, from reading the sources at the time, it was known that one of the people was a sloppy and bad researcher, though he was a renowned professor, and the other one, who was not a renowned professor, was a very precise researcher. So I think we cannot deal with this as philosophers or as historians without knowing really not only the scientific experiments, which we cannot judge by ourselves, but without knowing more about the people involved and to look at their practice and at the reputation they had at the time.
Well, there's one part of that I would disagree with, that I don't think you can judge the people involved without being a member of the field. Now, I've written an awful lot about this stuff. My book, Changing Order, was about disputes in science. And I've also written a book called Tacit and Explicit Knowledge. It's not actually Polanyi-esque, it's more Wittgensteinian. But yeah, I mean, my first paper was about the tacit knowledge required to do a kind of to build a successful new kind of laser called a transversely excited atmospheric pressure carbon dioxide laser. And that paper is still getting cited, believe it or not, about 45 years after it was originally published. So yes, if you write to me, I'll send you, I'm afraid it'll just be a couple of papers in a reading list, but I've written an awful lot of stuff about this. So that book, Changing Order, is called Replication and Induction in Scientific Practice. But the latest argument that I'm putting forward, which you'll find in the book that is coming out in open access fairly soon, it is about the fact that science won't work unless it's done in small closed groups. That's one of the reasons. One of the reasons is that people have to get to know each other before they know whose claims to trust and whose claims not to trust. Now, I'm kind of notorious for getting so obsessed with gravitational waves detection research that I managed to pass as a gravitational wave physicist. And this is actually written up in a little one page in Nature that I managed to pass as this. But in the last book I wrote about the gravitational wave detection business, called Gravity's Kiss, I explained that the hardest thing that I had to learn in becoming knowledgeable about the gravitational wave field was who to trust and who not to trust when they made a claim. So I don't think outsiders can do it. You can't do it from track record, for example. But insiders can do it. If anybody can do it, it's insiders who can do it.
True, but you just said you learned whom to trust and whom not to trust. And that's exactly what I meant. But that is what outsiders can do, because they read the sources, they talk to the people, and they're
No, I only learned it by becoming an insider.
Okay, I've done it by becoming an outsider and by staying an outsider. I will report about that later on. I don't want to go on now.
And okay. Okay.
No, that's fine.
So I think you have a no? Okay. So any other questions? Maybe the people from Zoom? So there are no other questions, so let's thank Professor Collins.